Okay, so let's begin. The topic of my talk, yeah, first of all, I should mention that it's joint research with Valentin Lychagin, and it's also continuation of our previous, I think I gave this talk also here, on invariance of linear differential operators of second order. And today I will continue and we'll talk about some class of nonlinear differential equations of second, not equations, operators of second order. So operators will be the following type. So we consider some manifold M, dimension n and connected and stuff like this. An operator that will investigate, I will denote by A with a label W. It means that it will be weak nonlinear operators. So they look like this. Action on function f on our manifold. So this will be the following: sum aij's of x and f of x d to f dxi dxj plus ai's xfx ddxi of f and plus a0 xf multiplied on f. So this class of operators we'll call weakly nonlinear. So nonlinearity also only this of function f that presents in coefficients of this operator. What we know about this class, that it's so-called natural class. So naturality in my talk, it will mean that it's invariant under diffeomorphism group. And say natural invariance, it will be still invariance of diffeomorphism group. So diffeomorphism group of this manifold M, X on this class of operators. And what I will do, first we will discuss differential invariance of such type of operators. And the second we'll see how we can apply them to present both local and global classification of such type of operators. Okay. Together with this operator, I will use also without this f. So it will be, for us, it will be simply this expression. Weak.
Weak.
Yeah. It's yeah. So forget about this. It's okay. We can write like this. It's so it's written here. What we can say about this? This is a linear operator now, but it's linear operator on extended space. So I will use notations like or bundles. Let's use some letters, say, I don't know, and also linear differential operators on M, second order, it's simply section of this bundle.
Arbitrary. not weak, but
linear operator on manifold M is a section of this bundle. It's the reason to introduce this bundle. And the section of this bundle, it will be operators linear differential operator second order, but this special type. So speciality.
This is a pullback
No. I will discuss relations between these guys and these guys. What I said that before we study this bundle, so linear differential operator second order, take jets of this bundle, take rational functions invariant under diffeomorphism group, and they give us natural invariants of linear operators. I will not go in details here. It's just you can find in our paper. So I will use this part as a known part, and this we will investigate now. So this is the first type of operator that I will use, and the second, it's very funny guy. I will use notation AF, and this will be the following. I restrict this operator on the graph of F, so it will be operator of this type. So this operator, linear operator of second order on manifold M. So AF is lives here. It's an operator on M, and this is our operators of the form A. They just here. And relation between these three guys very simple. It's the action of operator AF on the function F. So first of all these constructions are natural in the sense that there is action of diffeomorphism group of our manifold M. This diffeomorphism group on M I will extend on M cross R. It's really zero jets of functions, so you can say that we simply extend in zero jets, take prolongation of diffeomorphism. But it means that diffeomorphism here on M acts on this product by trivial extension. So it acts on M, but trivial actually. So say x y goes to 5x y if phi is diffeomorphism. So what is important here? So this is class of operators that natural for diffeomorphism group. This class of operators, it's not good to say that it's class of operators because it depends on F. It's not operator, but it's pair of operator F. It's also there is obvious action on this type of operators, and if you just apply that, simply should also apply to this coefficient F by diffeomorphism. Now I will put all this together and see how we can get from this trivial observation way of finding invariance. So together with these two bundles, I will introduce one bundle more. So these three bundles will be important for us. So section of this bundle is the functions. Section of this bundle is linear operators on manifold M. And section of these bundles, these operators of the form of this form on the cross product. Now I will organize this in the following way. So I will take jets of all these bundles, say k jets, second and third one. So we take k jets of this extended bundle psi tilde. So there is projection. So this psi tilde k, it's a projection on the base, and base for our case is M cross A.
You mean that we take derivatives with respect to y also?
Here. Yeah. I didn't say this, but if you take our I remove this operator, so this operator. So what we should, so it means that I will put here f simply. What means that we have invariance of this operator, differential invariance of this operator. It means that it's functions depending on jets of Aij, AI, and A0, and this is jets in X and Y.
Yes.
So because coefficient depends.
N plus 1 dimension.
Yeah, and this function should be invariant under the diffeomorphism group, so it means that they invariant. So now I will put it in slightly different way. So I will take k jets of this type of operators, and this is my bundle. So elements here, this is k jets of operators and the point xy. So this, and also I will take k jets of the functions. It's our bundle pi, and there is so there is projection on the M, but I will take intermediate case. I will take here G0 of pi. It's exactly M cross R, and this is our pi projection of the M. And so from these two ones, this and this, I will introduce new bundle. It's the following. I will take
Pi is projection to M or to pi? Pi is projection to M or to pi?
Oh, sorry, to M, yeah. Yeah, it's a functions, it's a projection, yeah. So what I will do, I will take, so this pi k0 projection. So I will take, there is two names, Whitney product and Whitney sum. In this case, this fibers, this vector bundle, so the fibers here vector spaces, and bundles here, fibers here also vector spaces. So I will take the sum, and we'll call this Whitney, something like this. But so it's should be pairs this one k jets of operator and k jet of function. To the same point, yeah. But you see, yeah. But I will restrict myself to pairs that y not arbitrary, but y is equal 0 jets of f. So it means that I will take point here, and this point 0 jet of f. And when I take this fiber, I will take not an arbitrary point y, but at the point x fx. And here there is this is k jets of psi at this point, and cross or plus k pk 0 minus 1 at x. So this is our bundle, double V K. So it consists of two jets, k jet of our operator and k jet of our function. But k jet of our operator we take at the point 0 jet of function.
But it means exactly that these two jets of K and F are such that they project to the same
point, yeah. But I will consider not arbitrary point here because I can take arbitrary point here, but it's not true here because if I have k jets, I know this it's fixed now for me. Anyway, this is three bundles, and I will call this pairs as a related pair. And now we'll do the following. So we have this is bundle psi over M. So this is all differential operators of second order on M, linear differential operators. And we have also here M, and we have this double V K here. Maybe we will put here KL because sometimes I will change these jets, and so it will be KK, and also I will take VKL, where L will be maybe more than K. So it also such pairs, but I will take K jets of operator, but jet of function maybe more than this K. But I will just take this one. And there is interesting map from this to this, from this to this.
The second bundle should be bundle over M cross R.
Second bundle.
W is over M cross R.
Yeah, thank you, but it's true. Because I should take projection on this level. Yeah, I can, but this is in this definition, it's only projection here, but certainly we can make it to this one. But anyway, we have this map from this bundle to this bundle. Let's call this, say, theta with the label K. And how it acts? It acts the following way. So I take pair here, K jet of operator A at the point X fx, and K jet of function at the point X, and put it in the K jet of this operator AF. This operator AF. So it gives me map from this to this. Yeah, but so the first remark, trivial but important. So diffeomorphism group acts on all these bundles. This one. Oh.
No, the bundle, not the space.
Give me letter. Give me letter. No, it's taken. It's forbidden.
No, not this one. I mean the arrow.
Ah, you mean this one? Okay. Okay. It will be capital and this will be small one. Yeah, so I construct this map from this to this. And this map is the following. So we take this pair, this our operator A, this our operator A, construct this operator A F, so put it here F, and take kjets of this, a kjet of function, and you will get this will give you operator, and after they take kjet of this operator, this one, it will be here. So what is important here that all these bundles are natural in the sense that there is action of diffeomorphism group of M on all these bundles. And this is theta, it's also natural, or it's natural map in the sense that commute with this action of diffeomorphism group of our manifold. So, and this is remark give us immediately an obvious step how to get invariance of our nonlinear or weakly nonlinear operators. I will take function, say here, I. It's a function. So it's functions that depends on kjets of our operators, linear operators on M. So it's leave. I will remove it. Okay, it's important, but it's easy to remember. So this is a bundle of jets of our linear operators, and our theta k. Yeah, because we take k jets, we need zero jets, but k jets. So this is the map that we have. Yeah, and we can consider like this. So you consider this as a bundle over M, and this bundle over M. Here there is action of diffeomorphism group. So this diffeomorphism group, and the claim is that this is map. It's commute with the action of diffeomorphism group. It's more or less. It's not trivial, but it's simply some straightforward checking. But what follows from this observation that if you take function on kjets for linear operators and take theta k star of I, you will get function here. And what is the function here? That if it was invariant on the diffeomorphism group, so it will be also invariant here. So it means that invariant of linear differential operators on M will generate invariant of related pairs, because here it's just related pairs. Now, what is the difference between invariance of related pairs and invariance of operators? When we computed invariance of our nonlinear operators, we took coefficients and take their jets, right, in X and Y. But we did not think that y is a function if we take not derivatives of this y, derivatives of functions. So in the sense that they invariants, but they depends on kjets of this A, but they do not contain derivatives of f. And if you take invariance here and take this pre-image, you will get invariant expression, but it contains both derivatives of coefficients of A and derivatives of function f. So in order to get invariance of our operators, we should do something with this invariant and remove all so make some kind of descent. So we should remove derivatives of function f that involved in our invariant. And to do this, we should do it in invariant way. So we should make this descent, but descent should be goes along differential invariance, natural differential invariance. So every time we should do it and did not lose invariance under diffeomorphism group. So roughly, if you just forget all blah, 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 so it's a very simple observation. So take your this operators. We remember we had this operator A, this operator AF, and omega. So because all these constructions, they're natural. So if you take transformation that goes from A to some B, then if you apply here, it's also will from AF to B, but not F. You should transform also F.
A is in X and Y.
Yeah, so
AW is
it's on. It's,
Y,
yeah,
and AF
it's all in. Yeah, yeah. So it will be goes to B, but also phi star of F. So you take diffeomorphism, and this so this is diffeomorphism. So operator A goes to operator B. Then operator AF will go to operator B, but not at the function f, but in this new function. So this naturality means. And so in other ways, okay, it's if you have some idea how to compute invariance of linear differential operators second order, then you can try to apply this knowledge to our situation. So you take this construction AF, take invariance that you can compute, but you will get something that will be really invariant. We will get invariant of diffeomorphism group, but the only problem is that it depends higher derivatives of f. So first, second, and so on. And if you will be able to remove this dependence on derivatives, then we will get invariant of our operator. Now, a little small piece of algebra. And maybe some extra requirements. So we will introduce some fields. Yeah, and as I said, we can take this one, or we'll take VKL with conditions that L more than K, because L is it's order. Yeah, it's order of f and this order of k. So in this construction, when we will do this, if it has order more than k, but you can use the same construction, simply forget about high derivatives. So now we have the following fields. So first of all, we have simply functions on kjets of xi, and I will use infinite jets. So let's take infinite jets of Xi. So take, okay, let's take the final case. So first of all, let's take field of functions on this manifold. So it's manifold of kjets of Xi. Yeah, so kjets of Xi, yeah, and there's a standard condition. It's simply non-linear differential operators. The functions, the value. Yeah, so we take the differential operator, compute it. Okay. So, but one point more that I will consider functions that rational along this fiber, but I will one more remark. Because fibers, they are vector spaces, so rational functions on vector spaces.
No, but they are functions of M.
No. It's a function here.
Functions from F programming. Yes, I understand. Yes.
So we take functions here, and the requirement that if you restrict on the fiber of this projection, they should be rational. Yeah, sorry, but it's here on R, right? Oh no, Xi. Oh, it's Xi tilde. I'm sorry. Okay, let's do the F tilde. Oh, this one. Okay. I'm sorry. I will consider, because it's not. I no need this Xi tilde. So this will be these functions here. Yeah, this is one, and it's projected on M on R. So I will require rationality in this fibers. It's more or less standard situation in invariant theory. It follows from this version of Lychagin theory, and then we investigate situation when invariants are rational functions along with fibers. Then it's place where Lychagin really varied. Yeah. But really, we will add a little more. Why a little more? When we study invariants of some group, say group of diffeomorphism, then because it's invariant, it's enough to consider they only at the one point of base. But if your action on the base is a transitive, then it's true. But if action of your group on manifold is not transitive, then requirement of rationality will not follow from anything. It's just what I want to say, that if you will consider invariant, rational invariant under this projection, it's not enough for me to continue, because all our constructions really will be, depend our group of diffeomorphisms act intransitive. Yeah.
Here, yes, of course.
On M, да, but here it's not. So, so it means that I have natural notion of rationality here, but not rationality on the M. And so this will be my extra condition. So I will consider functions which are rational not on this, but rational up to this point. So in another way, I will consider, after all, invariants of my operators that are rational in this wire. And but now it's a question about what kind of operators I should consider, because when I will take my operator and restrict invariant on my operator, I I want to get something also algebraic, some kind of rational. And it means that my operators at the beginning, I should require that they are not arbitrary, but they should be rational in Y. So this operator A is that I write coefficients of this operator, they should be rationals also in Y. Then
These A's, yes, the coefficients
of operator A.
should be rational, arbitrary in X.
Yeah, right. So this is just, it will be important for us when we will start to use algebra, and we really need fields, and these fields, it will be fields. I will not bother you with some extra conditions. Really, it can be algebraic and Y, but for us it will be enough to require that it's rational. So this is what we. The first field that we will consider, this is this one. Really, I have together with my this bundle, I have this bundles WKL. So they also bundles over M cross R, but I will continue to M, and I will consider functions that on this bundle that function of this bundle that also rational along these fibers. And this will be our, say, F, let's do once more tilde, KL. In reality, K will be not important for us. The more important for us, as I said, the more important that we should find some way to kill dependency on higher derivatives of F from our invariants. So it means that instead of this finite, I will use infinite jets, and instead of this, I also will use it, say 5 tilde simply L. I will take limit with K.
So Fk is the case when K equals L, yes?
Yeah.
FKL is
It's L means it's order of jet in function F. So it means that this is functions that depends on K jets of our operators, and yeah, and L jets of function F. Yeah, but after this, I also will remove this K from consideration. I will consider this. So it's functions that functions on infinite jets of our operators A and having L order in F. Okay, now we will what we will do. We will take invariance in all these cases. I don't know how to say. Let it will be say Q L, and here Q point. So it's simply invariance of action diffeomorphism group on this field, and this invariance of the action of diffeomorphism on this one.
You mean these are functions invariant
Diffeomorphism group. It will be not very important for us, but this guy will be important for us, and this guy also Q0. Huh? Yeah, fiber. All them fiber-wise. Fiber means up to the last point. So it's invariant functions on jets of our operators involving L jets of functions invariant under diffeomorphism, and this is involving only zero jets of functions, and this is exactly invariance of our weakly nonlinear operators.
But you told that L should be greater than K.
Yeah.
But here we have infinite order in K.
No, it's here, but not here. So sorry. Here there is no real restrictions on L and K, because it simply means that I will consider what depends on K jet of my operator and L jet of function. But our map of this that we discussed, it really can be constructed in the case when L bigger than K. But in this field, it's defined and also when I just say that I forgot about order in K, it was simply it's a function that depends on L jet of our function and K jet of our operator, or some jet, it doesn't matter. And so what it is, it's will be simply functions that depends on K on jets of our operators. They do not contain derivatives of our f, and they invariant under diffeomorphism. So it's exactly what we looking for. So this invariance of our weakly nonlinear operators. Now, what kind of relations here? So this guy is it's here, and Q0 it should be something like this, right? And what is the relation between these two fields? So this is field that it doesn't matter how it depends on jets of operators, because we simply say that any orders included here. And this is contains L jets of functions, and this is contains only zero jets of functions. So the statement is the following: that certainly this is a part of this. So this is this subfield here, and the statement, because what is the transience degree of this field over this one? I know. It's because it's exactly this, because what is the difference between this is depends of derivatives of function f up to order L, and this is only zero order. So if you consider this, you see that to get this, you should add all derivatives of first order, second order, up to L order, and this will be just the transience degree. So this is really this one. So what I want to say is that this field, it's a finite extension of this field F0. It's not the whole story. There is one guy, very funny. It's some derivation in the field this F tilde L. So what is about this field? So it contains jets of operators and jets of functions, and we have this coordinate y. This is a fiber of projections M on R on M.
Sorry, what is number?
I just will define it's I will define some derivation that x in this field. So what is the derivation? So I have this y and I have a vector field ddy, vertical field here. So and I'll simply let's write dy. So I can take this dy and take its else prolongation. Then I will get derivation that act on exactly on L jets of functions. Is the one derivation that acts on only the functions, but it's not yet act on jets of operators. Now I will take this is the total derivative, like this, and this is this total derivative with respect to y, it gives me derivation on jets of differential operators.
Infinite.
Huh?
Infinite jets.
Yeah, infinite. Yeah. So I remove this order. So I have derivation on parts that corresponds to jets of operators and this one, and the part that corresponds to derivations on the jets of functions. So if you take that and their product, in the sense that it should be something like this. And so this derivation, this is our nabla. This invariant under the diffeomorphism group. This is invariant under diffeomorphism group. This invariant derivations in this field FA. Now let's try to construct invariants. So we take, as before, invariant I. It's a invariant of linear operators on M. Apply this is theta, and we'll get this is, let's call this I0. This is theta k star of I. So we take differential invariant of operators of order k, apply this map theta, and what we'll get, this will be invariant of related pairs. So if I just forget, so it means that it involves k jets of operator and k jets of function. But I will consider this as an element of fk. Right? And let's so this is this guy. Now I will take I1, namely I will apply another. Why?
Because you should put k equal to infinity.
Oh. No, it's here. It's when I put here, it means that I forgot about order of operators. It's only k. It means k jet in function. No, it's derivation here. So I use this. So I apply this derivation. I will get this invariant. I apply this derivation. I will get this invariant, and etc. So all of them, they are elements of this field. This field has this transient degree over this our F0. So it means that between any, let's call this say, I don't know, n is not taken. So if I take n times this derivation, I will get n plus 1 element of this field. Because transient degree equal n, it means that it should be some algebraic relation between them, polynomial relation. So it means that I will get polynomial of I0, I1, In over this field. With coefficients over this field. What not
maybe even earlier.
It's true. But I said that it's certainly this one, but it maybe depends on less than this one. Yeah, so this is polynomial in over F0. So if you take, okay, let's move it here. So we should consider now the polynomial polynomial ring over F0 in this n plus 1. Oh, sorry, one small n should be capital. And if you consider all possible the syzygies relations between our invariants, we will get here some invariant. Sorry, ideal J. Oh, huh? It's for formal varieties. Yeah. It's just instead of this one. So we will get some ideal in this algebra. What I can say more? What we have in this? First of all, the diffeomorphism group act in trivial way here, right? It's because it doesn't change this invariance. The second, we have here lexicographic ordering. Like this is the first one, the second one, and this is natural ordering. It means that once more diffeomorphism group will be not change of this ordering. It's just because with our construction. Now we will use. I am not big fan of this. We'll use Gröbner basis for this ideal, and we know that if you have lexicographic, let's say with lexicographic order, if you take Gröbner basis, and if you say it should be reduced in the sense that we should take only polynomials with leading term equal 1. So this is a basis, let's say B1, B, I don't know, doesn't matter. So this is just a reduced basis for this ideal. And once more, in this Gröbner procedures follows that it's unique. This basis is unique. If you fix it ordering and then you will get just unique this, and it will take that this should be reduced to polynomials. So what we can say, our diffeomorphism group act on these ideals because it preserves relations. The second, it's also act on these polynomials, and because this basis is unique, so it will not change the basis. This polynomial, so coefficients of this polynomial, action of our diffeomorphism group will act only on the coefficients. And it means that coefficients should be invariants. And coefficients will be from here. So it means that we will get invariants our operators, weakly nonlinear operators. you can use computer to it's it's constructed in the sense that there is simply algorithms that allow to use this. Yeah, so certainly in the given case, computations can be too long or maybe simply impossible. There is algorithm, but maybe it will take, say, 100 million years to finish. But it's the only that I want to say that knowledge of invariance of linear differential operators second order on manifold M allow us to find invariance of
Understand why with second order is seen.
yeah.
Only the first moment.
Ты забираешь у меня хлеб. No, second, why second order? Because for second order, we know exactly how to find invariance of
All the scheme works
for any order. But how we find invariance for second order? We take operator, take symbol, it gives you metric. And don't generate a metric. Then you can use Lychagin connection for the metric. So you split your operator in sum of tensors. And then the question about invariance, simply questions of invariance of these tensors. And it's...
yes, I agree, but up to this moment, we saw no...
No, it's, yeah, I agree with you, but I just will continue. Yeah, we agree with you that if they consider not arbitrary, but regular differential operator second order, there is a way to find the invariance. But if you take, say, differential operators of the third order, the first problem will be that we have no idea how, except two-dimensional case, we have no idea how to find invariance of linear such operators. We have only one case when you can construct this
Wagner.
Right.
Sorry?
Thank you, Boya. Wagner connection. So, yeah, it's Wagner found connection that related to cubic symmetric differential forms on plate on the dimensional manifold, and it's impossible to construct the Wagner connection in general situations. So there are some requirements for symbols. We call this constant type symbols. It follows that orbits of linear groups on cubic tensors, they just more complicated if dimension will be more than 2. So it's true that it works word by word for any order with only one condition, that we should consider not all linear operators on all quasi-linear operators of this weakly non-linear operators, but with some condition on the symbol. So the symbol should have this finite constant type. So it means that if you take symbols in 2 different points, it should be a linear transformation that transforms symbol from one point to another point. So orbit of symbol should be constant on the manifold. So for such type of constructions, everything will just go like this. Okay, so now, do I have time?
Yes, we do.
It's too much. Now, how to use this invariance to say something about operators themselves. First, it's a remark about linear operators, simply linear operators on manifolds. So this is guys. When we study invariance, we introduce such invariant operator, we use this, I don't know, square symbol or D'Alembert symbol for this. It's a differential operator in total derivatives of the second order, and it's invariant connected with with this bundle. So it is the following. So if you take, say, some coordinates, say x, it's coordinates of the A or the M, u ij, ui, and u0. This is coefficients of operator in these coordinates. So we can take this as a natural coordinates in 0 jet of our bundle, and so this on the base, and this is on the fiber-wise, and we'll construct this operator of the second order, and this is very natural operator. So this operator, it's x from the level of this of jets of order k to jets of order k plus 2. So this our nabla. It's from functions here to functions here, and it's commute with its natural operator.
General effect, we compare the bundle of free jets for some initial bundle,
Yeah. So if you take bundle of forms, you will get natural differential form. If you have bundle of operators, you will get natural. Yeah, right. Yeah. But huh? Yeah, right. Anyway, why it's important for us is the following. So it's written in x coordinates, and x coordinates, who knows what is x? So we assume that we have some invariants, say z1 and zn. Then we can write all these total derivatives in terms of 3C derivatives in z. So you can write this operator as a sum of say k ij e2 dzi dzj plus some k I dzi plus k0. All case are invariants. So and to define our operator, we can define it in the following way. We simply take coordinates with z1, zn, and after this invariance. If you use concrete operator, then this is invariance because this is independent. It's condition that, it's in general position. So then yes, certainly you can do this. So it means that if you restrict on operator, then this ki's and kij's and k0, they will be functions of that. And the claim is that really this function completely, at least locally, define our operator. And it's clear that if you have two operators, you take the same z's for one, you have the second. And if the diffeomorphism in z's is simply identity diffeomorphism because it's invariance. And the only condition that this operator is equivalent if this corresponding function is simply equal. So this is locality. It's give you so-called natural chat for your operator on manifold. Now you can cover your manifold by this natural chats, by this natural atlas, and then simply compare this to atlas. If you have the same the same chats, then it means that you have the same operators. Okay, now I will do the same here. Yeah, certainly I have non-linear operator, but I remember that I started with this linear operator A. So I can write this operator, but now as operator that acts not on bundle of linear differential operators, but this is simply operators of the type A on this psi tilde. And so once more we can repeat it the same, but we take this invariance and add one more. Say let it be K0. Okay, K0, Z0. And once more condition of that we have general situation, it simply means that they are independent, but now we have n+1 invariant. So this can be used as a restrict on operator. You will get coordinates on local coordinates on M cross R. Now you take all these invariants that you have. They also will be functions of this case. And once more, you have the same situations that this function should be the same. But one more remark: our transformations they doesn't touch the Z0. So and when we will get diffeomorphism, we will get diffeomorphism that certainly will preserve Z0 coordinate y. But yeah, if I do this, then I will get the diffeomorphism of this one, but not diffeomorphism of M. So now I should be sure that really this diffeomorphism is trivial on Y. And if you compare this is to your local coordinates to operators and the Z's, and we'll see that the transformation from one system to another system doesn't change this Z0, then it gives simply diffeomorphism of M. And so in other words, that if you want to know local structure of your operator, you need only n invariants. And it means that this is constructions that we discussed it with you. There's no need to compute all possible invariants, but it's enough to find only n of them independently in general position. Okay, I almost finished. Questions, comments, anything?
I have question.
Yes, please. Who are you?
Boris.
Yeah, Borja, you're welcome.
So my question is the following. So your approach to invariance from like as differential operators in n variables, right? X1 to xn, where there's also one more parameter y, which is function of f of x. But it's possible also to look to this operator A as differential operator in n+1 variable, x's and y, which have order 0 in y, right?
Yeah,
So it's like it's natural subclass. It's invariant with respect to those diffeomorphisms that you consider. So my question is the following: if we just take the space of jets of such differential operators, like say second order, in x and 0 order in y, and you just try to restrict in differential invariance of arbitrary second order differential operators in n+1 variable, right? So will you actually get all invariants?
No.
Like in other words, is this regular orbital?
No. It doesn't work because this is a single class of operators. The symbol of these operators will be degenerate.
So why is it single? I mean, I understand, of course, that like this metric will be degenerate, but like just from the viewpoint of dimension, is it actually drop of dimension of the orbit?
Dimension of what?
You consider orbit of diffeomorphism group, right?
Yeah, but operators that you mentioned, this is a singular orbit in action of diffeomorphism group on this type of operators.
Why is it singular? Is a drop of dimension of the orbit?
Yeah.
Okay. Okay.
It was the first attempt or first step that we wanted to do. Yeah, it's nonlinear problem related simply transform into linear problem. So what's the problem? Okay, just start to compute this invariance, but yeah, but it doesn't work because we will get a singular case and we will live in singular orbit and how to compute invariance there. So really all this stuff, all this technique is just simply to avoid the singularity.
Now, I mean, just for there's technical problems that metric, like the symbol is degenerate, but this formally is just technical problem. I talk about like all invariants. And so like orbits may be in principle regular. So you have to compute dimension and compare. So this technical problem doesn't tell you actually that orbits are singular.
With singular symbol, they are singular orbits in differential operators.
I mean, this only can be, that's not obvious from the fact that symbol vanishes.
What do you mean not obvious?
The orbits are singular.
No, it's single body. It's you can simply compute orbits with, but dimensions, and you'll see that the dimension will be just different. It will drop it.
Okay.
I have
Okay.
a question.
Good.
Think about it. Is this published somewhere?
It will be published. It is accepted. It's now in differential geometry, in geometry and physics.
In physics.
Yeah, it's. I know that Valera promised me that he will put it on in archive, but I'm not sure.
I didn't see it.
Anyway, it's we got a referee report. We check it for English, correct it, and now it's in production.
Okay. More questions, remarks? No more questions. Okay, then thank you very much. We'll make a break for 2 weeks. And I hope that we shall meet in May. Goodbye.
Goodbye.
Thank you.
Можешь по-русски сказать?